Okay, today we're going to work through this Hexagon Mother's Day gift, and there are 10 problems here, and we'll just work through them. The first problem is on a separate sheet of paper, draw a regular hexagon to scale with sides of 3 inches. So let's start with the blank piece of paper here. Hexagon is a 6-sided figure. Regular means all sides are the same. I want it centered on my page. Paper is 8.5 by 11. So I'm going to start right in the middle of 11 at 5.5, and it's 3 long. So I'll go 3 this way, or total of 3. So there's a 3-inch centered on the bottom, and I'm trying to be as square as I can by keeping my ruler on the bottom of the page. Then I'm going to use a protractor. Actually, let me just sketch a little hexagon here first. So just a rough sketch. 6-sided figure, all sides are the same because it's regular. I know that the sum of all angles in a triangle are 180. And here's another triangle with the sum of 180. And then this is 360. So all 6 interior angles are going to sum to 720. I have 6 interior angles. I divide 720 by 6 and I get 120. So each interior angle is 120 degrees. So I'm going to use my protractor and find 120. There's 120. That's just a little construction mark. Do the same thing here to find 120. And then the sides are 3. So I'm going to set the 3 right on the end point of this line and go through there. And there's my 3-inch mark. I'll do the same thing here. Going through that 120 degrees. 3 inches. Then the next one I'll do again. So my protractor here, interior angle is 120. Interior angle here is 120. And again, side of 3. And a side of 3. So when I close these 2 endpoints here, it should be 3 inches, a little bit off. Okay, so there's my regular hexagon with a side of 3. Next thing, question 2 says, draw another hexagon inside the first where sides are 2. So I want to go like this where all sides are 2. And then it says the distance from vertex to vertex is 1 inch. So I'm going to come in 1 inch here and create a trapezoid inside my hexagon. So for that to work out, these are all going to have to be 60-degree angles. So here's 60. And I'll mark a 60 here. And I'm only coming in 1 inch. So I'll set that. Now this should be 2 inches. A little bit off there. Yeah, and that is 2 inches. So connect that. And these are 2 inches. So this is a 2-inch length. This is a 1-inch length. And this is a 1-inch length. I'll do that all the way around the outside. Okay, so I finished my regular hexagon. So here's my interior hexagon with sides of 2. There's a trapezoid, isosceles trapezoid at the base with a 2. And this is a 3, and these sides are 1. Question 3, the hexagon should be made up of 6 equal trapezoids. What are the angles and dimensions of these trapezoids? 60, 120. Number 4, if I draw a square around the outside of the hexagon, what kind of triangles are the cutoffs? So that's these triangles here. So I just drew a line right on top of that, perpendicular, to get the rectangle that covers this. So this was 60. This is the same trapezoid as 60. This is a straight angle. All this has to add up to 180. So 180 minus 120 gives me this is 60. This is a right triangle. So if this is 60, this is its complement at 30. And I have a 30, 60, 90 triangle. You might remember those from geometry. A 30, 60, 90 is really common. The side opposite 30, if it's 1, then the hypotenuse is 2. And the side opposite 60 is always the shortest leg root 3. So in a 30, 60, 90, we have 1. Opposite the 30, hypotenuse of 2. Opposite 60, root 3. If this were an x, this would be 2x. This would be x root 3. So I have a 30, 60, 90 triangle. I could also use trig, or know my 30, 60, 90. If the hypotenuse is 3, now the side opposite 30 is half that. So that's where 1.5 comes from. The side opposite 60 is 1.5 root 3. I could just get a decimal approximation on my calculator. 1.5 root 3 is 2.6. So in this 30, 60, 90 triangle, I have a side of 1.5, 2.6, and 3. Okay, so this is number 4. What kind of triangles are the cutoffs? What are the ratios of sides? And so it's a 30, 60, 90, and those are my sides. Number 5, number 6, the lumber this frame is made out of is more expensive as the board gets wider. What's the narrowest board I can make this hexagon frame? If I look at this dimension here, I can see this dimension is 2.6 to here. So this is also 2.6. So the overall width this way is 5.2 inches. So if I make it this way on the board, it's 5.2 inches wide. But if I make it 90 degrees this way, it's 1.5, 3, and 1.5. It's 6 inches. So if I make it lengthwise on the board, I could get away with 5.25 inch board because it's 6 this way on the rectangle. So number 7, if the board is $4 a board foot, so the board's $4 a board foot, how much does it cost in lumber materials to make this? Well, you could do this a few different ways. The truth is you're probably going to end up throwing these triangles away. So you could just use a rectangle 6 by 5.2. So 6 times 5.2 is 31.2. And it's 13/16 thick. 13/16 thick. So I'm going to multiply that by 13/16. And that gives me 25.35 cubic inches. So that's 25.35 cubic inches. A board foot is 12 inches by 12 inches by 1 inch thick. It's a volume measurement. So 12 times 12 times 1 is 144 cubic inches. So if I do the 25.35 divided by the 144 cubic inches, I get 0.17 of a board foot. So that's how many board feet I have. I take that number times the $4 per board foot, and I get about 70 cents in lumber costs. You could do it that way as a rectangle, or if you want to find the area of the trapezoids, you could do that and multiply it the same way out. But the truth is it's going to be really hard to use these little triangle cutouts for anything. So even though the board could be 5.2 inches wide, number 8, how long does it need to be? It needs to be 6 inches long. How many of these parts could I lay out on 11 by 2 foot board? Let me draw that out. Let me stay in the same units. So if it's 11 by 2 foot, I'm going to just convert 2 foot to 24 inches. Each board, each hexagon could be 5.2 wide. So I could go this way. I could go, 2 across, and they'll fit that way. And then these are 6 long, so I should be able to get 4 of them in here. Of course, that's assuming there's no blade cut width. So I should be able to go 4 by 2, or I should be able to get 8 actual pieces out of a board 11 by 2 feet. And then the last question, in the inside hexagon, we're going to create a pocket. So this is a pocket cutout. So this is a pocket cutout right here to put my piece of plywood with the engrave into it. And this piece of plywood right here is, 20 thousandths of an inch thick. The lettering, that blue sparkle paper underneath, is 15 thousandths of an inch thick. So the total thickness is 35 thousandths of an inch. So the pocket should be 35 thousandths of an inch deep. How much wood's remaining after I remove 35 thousandths? Well, the wood thickness is 13/16 minus the 35 thousandths. And I'll do that on my calculator. 13 divided by 16 is 0.8125 minus 0.035. And I end with a thickness of 0.7775 of an inch. So that's how thick the board should be. All right, so that's a performance math task, working with hexagons, trapezoids, triangles, area, perimeter, volume, ratios of sides, measurement, layout,